Welcome to our lesson on linear measure. We're going to get started. Let's start by a couple of vocabulary words. We're going to do array first. So array is what I just call a half of a line. Half a line makes array. So to be half a line, you have to see that you're going to have an end point, and then you'll continue like a line, but only in one direction forever. To name array, we start by always naming the end point, which is point A, and then a second point on the array, any point at all, anything that it passes through. So starting at A, it passes IC through Y. So I would call this ray AY, and I use the symbol for ray, which is that the single-headed arrow. Now, you'll see also there's a point B. So a second way to name this ray would be, again, starting always at the end point, A, and passing through B, using that same ray symbol. Every point is picked up by starting at A and passing all the way forever. All right, a line segment is a really important object in geometry because it's the first thing we actually can measure. And a line segment has what you see here, two definite endpoints. So a line segment is a part of a line, and we say it's the part of the line contained between those two endpoints. Now to name a line segment, you do name 2 points as well, and it's the two endpoints. So this line segment could be named line segment AB with just the symbol for line segment, no arrows. Or, since order doesn't matter on this, we could also name it BA. You just, again, name those endpoints. And a final vocabulary word, the word congruent. We're going to be looking at things all year long that are congruent. So what does congruent mean? Well, simply it means it's two figures that have the exact same size and shape. So we're looking for same size and same shape. So some basic examples would be like if I drew a simple heart figure, if I was talented enough to draw it exactly the same, identical, that's not too bad, then I would say these are congruent. I would use the symbol for congruent, which is an equal sign with what my students call a squiggly on top. So this symbol here is for the word congruent. And those two hearts have the same size and the same shape. So an example of not congruent would be a heart and then maybe a bigger, long, elongated heart. Definitely not the same shape, you could argue, or the same size, you could argue maybe the same shape. But these are not congruent. And so I use the symbol for not congruent by drawing the symbol for congruent and then slashing through it, a lot like not equal to. So congruent means same size and shape. Your hands make a really good example of that. They can be brought together, same fingers, unless you had some tragic accident in wood shop or something. Generally they have the same size and the same shape, so they're congruent. Now, to show that figures are congruent, we can do a couple of things. The typical thing is if they're line segments like these, you can look at the measurements of them, and you can see that by the numbers, there are two of these line segments that are congruent. So I would say that segment AB is congruent to the bottom segment, segment AC. So there's my congruent symbol and the name AC. Those are congruent. Now if I want to mark in a picture that they're congruent, I can definitely just use the numbers, but I also use what we call tick marks, and those tick marks look like this. There's a set of tick marks, and I just mark them the same to say that those two sides or segments would match. If I have more than one, as you can see in this figure, you just use more than one tick mark. So you just want to make sure the number of tick marks that you use matches. So in this picture, I see 2 tick marks on DH, segment DH would be congruent to this segment GH with also showing those 2 tick marks. And likewise, 3 tick marks are marking DF, so segment DF is congruent to segment FG. Now I'm going to jump back a little bit. When we see these numbers here, we want to say that those measures are equal, just like a measurement is a number, so it would be able to be equal. And in that case, I would use this designation. I'm going to use AB with no symbol at all. When I do that, I'm saying distance from A to B. And this is kind of an important idea, so I'm going to note it. That's read as distance, or the measure from A to B, or the measure of A to B. So if you don't see a symbol over those 2 points, then you are talking about the measurement of that line segment. So the distance from A to B, that would equal the distance from A to C, Again, I'm not going to use a symbol. And both of those are equal to the value of 2 units. Okay, so let's move on to a postulate. You'll remember that a postulate is a statement of fact that we just accept as true. And this is our first one for segment addition, the segment addition postulate. Let me read through it with you. And this is a chance for you to grab some colored pencils as you take notes. They really can come in handy. So if you need to pause the video, go ahead and do that. Grab a few colored pencils. Okay, the segment addition postulate reads this way. If points A, B, and C are collinear, so they're on the same line, and point B is between points A and C, then, again, there's distance. The distance from A to B plus the distance from B to C would equal the distance from A to C. So let's see how that works out in our picture. I'm going to mark on the picture the distance from A to B in red. So here's the length of segment AB. When I go back to my statement, I find the distance from B to C, which I'm going to mark in blue, is this portion, or this length. And then finally, the distance from A to C, I'll go ahead and mark that in a green. And that would start from here and move all the way across the full length of that segment from A to C. So this postulate is simply saying that if I take the red piece and add it to the blue piece, and they're on the same line, then it's just going to simply give me the full length all the way across from A to C. And let's see how that would work with some numbers. So let's say that AB is 2 units long and BC is 10 units long. How long would you expect AC to be? And this should be easy. Remember, this is a postulate. And just as the formula says, it'd be 2 plus 10, or a length of 12. So from A to C, we would expect it to be 12 units long. So that's the segment addition postulate. Let's see how it works in some examples. Our first example says that 3 collinear points, M, H, and A, and M lies between H and A. So that would mean, as we draw our sketch, that I could have those 3 points all on the same line. They're collinear. So let me just sketch them. I don't know exactly where, but M is between H and A, so that means M is going to be this point, while H and A are the 2 endpoints. I better zoom out. Let's try that again so you can see it. Okay, so there's my picture. M again is between H and A, and they're all on the same line. Now, what does the segment addition postulate say on our sketch? Well, it essentially boils down to this. The 2 pieces added up make the whole thing. So it would look like this. H to M, distance from H to M, added to the distance from M to A is going to equal the full distance from H to A. Now, as we go to part C, we have some numbers to plug in. If H to M, that distance is 18 centimeters. I like putting that in the picture. And H to A is 29 centimeters. H to A, that's all the way across. Let me draw that below. And that's 29 centimeters. What's A to M? So what's this? And I'll put a question mark on that. Well, you might be able to see exactly how to do that, but let me go ahead and plug it into the equation. It said H to M, that's 18. Add that to M to A, which we don't know. It's our question. And that's going to equal our grand total all the way from H to A of 29. So how do I solve this? If this was an X, for example, you might do some algebra, but we're just going to bring that 18 over by subtracting 18 from both sides of that equation, and that means that the M to H, or no, excuse me, the M to A length would be a total of, I can't do that math. Let's see, that's 11, I believe. Correct me if I'm wrong. So A to M would be 11. A to M, distance from A to M is 11 centimeters. These were in centimeters. All right, let's take a look at another example, number 2. In this one, we see that point T lies between points A and B. Same kind of thing as before. That means, and I'm going to draw a sketch, that A and B are our endpoints with B somewhere between them. Distance from T to B is 3 inches. Let's add that to our sketch. And A to T, or segment AT, there's that congruent symbol. Segment AT is congruent to segment TB. I probably should have read this before I drew the picture because they definitely don't look the same length. So I'm going to make them look a little bit better. Let me move A out here a little bit. To remove all doubt, I'm going to tick mark or mark that these 2 segments are the same. And I'll use my colored pencil. and we're finding AB. Well, let's go back a little step here. If these are congruent, then remember that means they have the same size and the same shape. So if they're the same size and one of them's 3 inches, the other one's 3 inches. Easy as that. So let's add that in. So how long is it from A to B? Well, that's the full length. A to B would be the 2 pieces of 3 plus 3, which would be a total value of 6 inches on this one. And our final example. On this one, we have point E lying between points G and O. I'm not going to make the same mistake, and I'm going to read the whole thing before I draw it. From G to O, it's 17 units, and from E to O, we have this algebra expression for that, so we'll get to that, 3x plus 5. And G to E is another algebra expression. Find all unknown segment lengths. So this is definitely one for a picture. Okay, so starting off, we have point E lying between points G and O. Let's put G and O on the outside with point E between them. Now some measures. G to O is 17. That's all the way across. E to O is 3x plus 5, so E to O goes right here. I'm going to put 3x plus 5 on that. And G to E, that one is this segment. G to E is 4x minus 9. So my plan, I'm going to add these two smaller parts together and just call them equal to the full length of 17 units. As the segment addition postulate would say that, it would say from G to E added to E to O is going to equal the distance from G to O. So we just have to make some substitutions. G to E, they told us, was 4x minus 9. Add to that E to O, which we were given to be 3x plus 5. And the full length is G to O. That's equal to 17. Okay, now we've got some algebra to solve this equation. Let's find the value of x. First step is to combine these like terms. I see a total of 4x added to 3x's. Gives me a total of 7x. And then on my negative 9, add a 5 to that. I'm up to negative 4. Bring that down. Next, I'm going to add 4 on both sides to make this 0 out. So now I'm left with 7x equal to 21. And then finally, I'm going to divide the 7 off and bring that down, reduce it down to just 1x equals to 3. And so I know x is 3. Now this is geometry. We don't usually stop with the value of x. We usually need a measurement. So we're going to take that x value and plug it back into our expressions. So let's start with GE. GE was 4x minus 9. So I'm going to make the substitution 4 times 3 minus 9. 4 times 3 is 12, and take away 9 from that, we're looking at 3. So G to E is 3, and then E to O. E to O was our 3x plus 5 expression, and x is now 3, we have found, and so we've got 9 added to 5. 9 plus 5 makes 14 for that total. And I love this because we can check our work. Do our two pieces, 3 and 14, add up to the right value? So if this is 3 on G to E, and this is 14 here from E to O, do they make our grand total of 17? Of course they do. So it's awesome. So that's how you do linear measure and the segment addition postulate.